So, hello everyone. So, today we are going to have another Novice Camp lecture. Unfortunately, we couldn't do anything with the class with CodeSafe starters, but because of the strict schedule we have, tomorrow, tomorrow's lecture will be postponed to day after tomorrow. And today, so we are Inter-IIT Competitive Programming Conclave, which brings about 60 to 70 institutions together. And we are here with the camp, which is going on for 2 months, camp on competitive programming. And it also develops you the methods you need to apply in this different platforms, whatever you practice for competitive programming. So I'm here, Ayush from IIT Madras with my colleagues Aitya Misra, Gauris Baligo, and we are all here to bring a lot of lectures and practice problems to you to develop your skills in competitive programming. Nothing would be possible without our two sponsors, 0xPPL and Algozenith. So Algozenith is a premium platform for interns, placement preparation, and several other programs like DSA development, competitive programming projects. So the founder and mentor Vivek Gupta, he had taken one session for us as well. And we have another sponsor, 0xPPL, which is a crypto and Web3 company started by Prasanna Sankar, who was earlier founder of Rippling. He was rank one in India in top coder ACM, ICPC Code Jam, and several other stuffs. So you can join 0xPPL if you are excited about career opportunities in startup. You can mail to him at prasanna@0xppl.com to connect. He will be more than happy to have you. Now, we are here today with the recursion lecture. It will be recursion and backtracking by Dhruvil Kakadiya. He is international master, and I think you would have seen him multiple times in the camp. So he's one of our key organizing member as well. And we will be having so one more thing that is important, like the Novice camp will be ending by next week, most probably by Saurya's Pandey's lecture. I will once talk with him, and then there will be 1 week left. So if you have any suggestion for any extra Novice camp lecture, you can mention in the Discord server or WhatsApp groups. We can think about. So today we can start with the lecture. It's one of the very important lecture on recursion backtracking. So can we begin with the lecture, Dhruvil?
Yes.
Okay.
So, hello everyone. If I'm audible, then please write a +1 in the chat so I can confirm that I'm audible. Okay, I think I'm audible. And so let's see what is recursion. So recursion is related to a mathematical induction. Mathematical induction, I hope everyone already know. And in a recursive definition, you can say that an object is defining itself, and you can see that sets, function, and sequences can be represented as a recursion. And if you want to see that what is the real world example of the recursion, then uh, the image that mirror in the mirror, like if you place a mirror in front of mirror, then you can say infinite number of mirrors in, and that is also a recursion. And so that's the basic definition of recursion. And in programming, we say recursion, it means a function calling itself. Like in a program, you write some function, and that function is again calling itself from the function itself. Like let's see here. So let's say we have some function f, uh, that is of type void, let's say. And if I just call a function again by passing some another value, let's say y, then we can say that it's a recursion. Like here I can define y is equal to anything, like let's say 2 into x, etc. And now I'm passing y again. So from this line, the function will call itself, and the another replica of function will be built in the stack, and the process will begin. And after that function will complete, you will come back to the previous function, and then the remaining calls will run. Let's first understand what is recursion, right? Like what are the terms in the recursion, etc. So let's understand that by a basic example. So here is one example where a function x is written, and if x is equal to 0, then it's returning 1. And if uh, else it is returning y, where y is equal to 1 plus f of x minus 1. Now let's see how the what are the important terms in these recursion function. So first of all is a basic base case, where in the base case you define a constant computation and not calling the function itself. Like you are not calling recursion again. That means if you are not calling the function again, then the function will stop when it reaches x is equal to 0. Like you can see here, like if I am calling f is equal to 3, then 3 is not equal to 0. So the else condition will run. Here in the else condition, y is equal to 1 plus f of 2. So it needs to run compute f of 2. So it will create another replica of the function, and f of 2 will run. Now in the f of 2, 2 is not equal to 0. So again, y plus f of 1 will be called, like it's it's calling x minus 1. In f of 1, again we can see 1 is not equal to 0, and it will call f of 0. Now we made the base condition, like in the base condition x is equal to 0. So when x is equal to 0, we are returning 1 here. Like you can do these, uh, there will be other conditions, like we will return something else after computing something, like if x is equal to 0, you have some another variables and returning their stuff. We are just understanding what is the base condition. Base condition works like it's stopping the recursion function. So after it will return 1 and not calling any other function, or not calling function f again. So recursion will stop, and 1 will be returned to this call f of 0, and f of 0 returned 1. So 1 will be provided here, and y will be returned here by 1 plus 1 is 2. Now 2 is returned, and f of 1 is equal to 2. Then y will be 1 plus 2, 3. And 3 will be returned to f of 2. Now here, the 3 will return from here, and 1 plus 3 is 4. And that's how the answer of f of 3 will be 4. So what is the base condition? Like it's stopping the function from calling itself and prevents infinite recursion. Like let's say there is no base condition, then it will call the function again and again until, like it will call infinite time, because x minus 1 will run infinite time. And so it's simply the simplest form of the problem. I wrote this line because by recursion, we are solving some problems which can be reduced to some smaller problem. And in the base condition, what we will try? We will try to solve that problem in the base condition, and we'll return our recursion from that base condition and stop our recursion, and we'll solve the problem. And another case, important term is recursive case. Like in the recursive case, what we are trying, we try to move towards the base case. Like let's say my base case is if x is equal to 0 and I'm returning 1, but I'm calling x plus 1 here. Then it's obvious that I will never reach x is equal to 0 if x is not equal, if x is some positive integer greater than 0. So it will call my recursion infinite times and I will get some state space error, etc. And so recursive term means we are trying to move towards the base case via calling function itself. Like here you can say that x is not 0 and y is equal to f of x minus 1. So f of x minus 1 can be a recursive, is a recursive case because we are moving towards the base case. Now let's see how to decide that we have to use recursion in the problem. So first of all, we have to see that can a problem be solvable by recursion, and how we can see like the depth of recursivity calls is relatively shallow. Like in the recursion, we have to make sure that it does not exceed the space complexity and time complexity thing. And in the recursion version, it takes same amount of, it do a same amount of work in the non recursive version. Like let's see a problem. uh, let's say I have to print a number from 1 to n. Now, what is the iterative version? Iterative version is just run one for loop from I equal to 1 to n. And in the for loop, just print I. So that's our iterative case. Now, in the recursion, and the time complexity of this is O of n. That we know. Now, let's try to solve this using recursion to get more idea what recursion is. So, uh, I have I follow a basic technique to solve any recursive problem, and that is I told you that induction. We can see a recursion as a induction. So let's say uh, I am defining some function f of n. That's my first condition. Like I a condition to solve the recursion. Like this is my hypothesis. Let's say, and what I'm expecting that f of n do, like f of n must print number from n to n. So that's my hypothesis. And now what's my induction is, like if f of n is printing 1 to n, then f of n minus 1 is printing 1 to n minus 1. F of n minus 2 is printing 1 to n minus 2. So, and I have to make sure that this induction is true. And for that I have to define one base case, and the base case will be like I have to print 1 to n, and for f of n it's f of n minus 1, it's printing 1 to n minus 1. Like how we generally define base case, like let's see, here is a number line, let's say, and all the values in this part are valid, and all the value here are non-valid. So my base case must lie somewhere here. And as I'm printing 1 to and f of n must not go towards the negative direction. So my base case is near to 1, I can assume. So let's like, and I'm not printing 0. So my base case will be like if f of 2, then I'm printing 1 and 2. So I can say that in f of 1, I'm printing 1. So that can be my base case. Like whenever I reach 1, just don't call any f again and just print 1 and go back to and stop recursion. So that's how we print. Like we found our base case. Like base case is f of 1 equal to 1. That's our base case. And now, how we can implement this function? So we will just create one function f which accept integer n, and if n is equal to 1, then it will just print 1. Otherwise, it will, okay, sorry, and otherwise it will just call a function f of n minus 1 and print f of n here, print n here. So how this function will work, like if we call f of 5, then n is not equal to 5, so it will call the function f of 4 by printing 5 here. Not sorry, it will call f of 4 from here, from f of 5, f of 4. 4 is still not equal to 1, so it will call f of 3 from this function. It will again call 2 and it will call 1. Still the point we reach the f of 1, we didn't print anything. After f of 1 we are printing 1, so it will print 1. Let's say here is the answer that will be built after the function. So whenever we reach f of 1, it will print 1 here. After f of 1 is printed, we'll go back to f of 2 because it is not calling any function, so function will be completed and we will come back to f of 2. Now in the f of 2 we will print n, so we'll print 2, and same thing happens with f of 3. We will print 3. Same thing will happen with f of 4. We will print 4, and again we will print 5. So that's how we will print 1 to n using f of n. And for every problem you can like define these three condition, like sorry, you can define these three condition: hypothesis, induction, and a base case. Uh, and and in the base case we will try to solve a simple problem that's easy to solve and we know answer already. Like let's say uh, we are solving factorial. So in the factorial, what we know that factorial of n, let's say it's a function, so factorial of n is equal to 1 multiplied by 2 multiplied by 3 up to multiplied by n. That's how factorial is defined. Now let's see, I am returning in the reverse direction, and n minus 1, n minus 2 up to 1. So what is my hypothesis? My hypothesis for f of n, that f of n must return factorial of n. And what is my induction? That f of n is doing multiplication from 1 to n. And now, if f of n is doing multiplication of 1 to n, then f of n minus 1 must be doing multiplication of 1 to n minus 1. Pi is defined to multiply number. And so that's how my induction works. Like I know that f of n is multiplying 1 to n, f of n minus 1 is multiplying 1 to n minus 1. So f of n can be represented as n into f of n minus 1, as f of n minus 1 is multiplying 1 to n minus 1. And if I multiply that by n, so that's my f of n, because I just have to multiply n into the multiplication of 1 to n minus 1. So this is my induction. And what is my base case? Like base case can be anything. Like you say that you know the factor of 5 already, and just put that if n reaches 5, then just return the answer. Like let's say you know the factorial of 3, and whenever it reaches the 3, you will return that. And That's how you define the base case. So what is the minimum possible value that we know and we are sure about that? That f of 0 means factorial of 0 is equal to 1. And there is no factor of negative value. So factorial starts from the 0. So we know that f of 0 is equal to 1. So what we'll do now, that if we are calling function f of n, then if n is equal to 0, then we will just return 1. Otherwise, what we'll do, we will just return n into f of n minus 1. And that's how you can write the recursion. And it's easy to write and easy to see. Now let's see, we try some and what will be the recursion tree for this? Like you are calling 5, f of 5, then it will call f of n, f of 4 from here, n into f of 4. So, but n will be stored like let's say here, and f of the value of f of 4 is computed, will be computed. So from f of 4, you will call f of 3. From f of 3, you will call f of 2. From f of 2, you will call f of 1. And from here, you will call f of 0. And now from f of 0, you will return 1. So 1 will be returned and 1 cross 1 is 1. So it will be written here. And 2 cross 1 is 2. So it will go here, and 3 cross 2 is 6. And it will go here. 6 into 4 is 24. And it will go here, and here 5 into 6, 5 into 24 will be computed, and the answer 120 will be written. And that's how you can easily write any recursion function. Now let's try to do it for Fibonacci. So what is Fibonacci? So it's like, it's defined as f of n is equal to f of n minus 1 plus f of n minus 2. And the base cases are like this: f of 0 is equal to 1 and f of 1 is equal to, f of 0 is equal to 0 and f of 1 is equal to 1. So whenever we call a function f of n, it will call the function f of n minus 1 and n minus 2. And now let's see how to represent it in the form of recursion tree. So the function f of 5 is called, I'm just using, okay, f of 5 is called, right? From f of 5, two functions we are calling f of 4 and f of 3. Now, from f of 4, we are calling f of 3 and f of 2. Now, from f of 3, we are calling f of 2 and f of 1. Now, from f of, here is the same, f of 2 and f of 1. And from f of 2, you will call 1 and 0. And same for here, you will call 1 and 0. And same for here, you will call 1 and 0. Now we know the answer for f of 0 and 1. So what's the answer? For f of 0, it's 0. And for f of 1 is 2. And what we are doing? We are doing f of n minus 1 plus n minus 2. So 1 plus 0 is equal to 1. Now we know the answer for f of 1. It's 1. Now here again, f of 1 is equal to 1 and 0 is equal to 0. So 1 will go here. Now here 1 plus 1 is equal to 2. Now here again f1 and 0. So 1 and 0. Now again, it will go like 1 here, and 1 plus 1 is 2 again, and 2 plus 1 is 3, and 3 plus 2 is equal to 5. So the answer of f of 5 is equal to 5. Now let's visualize this thing in the visual go. Like here you can visualize many algorithms to see how things are working. So here is the recursion tree of factorial. Like we call the function f of 6, and it is calling 5, 4, 3, 2, 1, and 0, and the answer will go back to the 6. And let's see how things are working. See, the answer is going towards up again now, and the final answer is 720. Let's visualize Fibonacci number for n is equal to 6. So 6 will call 5, and uh, okay, 5 is calling 4, 3, 2, 1. 2 is calling 0. 3 will call again here 1. 4 will call 2 here, and the computation of 2 is going here, and you can increase the speed. You can see the direction of things are going. Like first the recursion is calling the function, then the arrow will go down. Whenever it will found a base case, the answer will go towards up. So that's how recursion work. And okay, now let's try to solve one problem on recursion again. So here is the problem from CACS problem name, and the problem name is apple division. So what we are given, like there are n apples with a known weights, like we know the weights of each apple, and our task is to divide apples into two groups, so the difference between the weights of the group is minimal. And here is the input. uh, it's like 3, 2, 7, 4, and 1, and we have to divide these in two groups. Like each apple can, let's say there are two groups A and B. So each apple can be a part of any one group. So let's say 3 is part of A, 2 is part of B, 7 is part of A. Uh, let's do it again. 3, 2, 7, 4, and 1. 3 is part of A, 2 is part of B. Again, 7 is part of 2. 4 is part of A. And let's say 1 is again part of A. Then what is the sum of each partition? If each group, like the sum of group B is 7 plus 2 equal to 9, and sum of group A is equal to 3 plus 4 plus 1 is equal to 8. And so the difference between two group is 1. Like we have to make the difference, like difference is 9 minus 8 equal to 1, and we have to return the minimum possible difference. Now let's try to define a hypothesis first for the problem. Okay, so hypothesis of the problem is like, uh, okay, first let's try to see what is the minimum possible thing you can do. Like let's say there are only two apples, two, and the value of them is x and y. Then either you will put both of them to the group A. The other case is you will put both of them to group B. And the other possible scenario is you will put one to the group A and put another to the group B, and you can see that the group number is group number doesn't matter. Like here, the sum of group A is equal to x plus y, and sum of group B is 0. And here sum of group A is 0 and group B is x plus y, but the difference is again x plus y. So A and B doesn't matter here. So that we know, and we know that if only there are if there are only two apples, then the best possible way is x minus y, right? Like we will put one into another group and one into another group, and the answer will be x minus y, absolute value of x minus y. So that's how we know the minimum possible answer. Now let's do a hypothesis thing. Like whenever I pass the array a, then I want that this function gives me the minimum possible difference between two groups. Minimum difference between two groups. And now what is the induction? Now let's say I pick the first element from the function, like from the array. Like here is the array A, and I pick this apple and put it into the group A. Then I just have to find the answer for the remaining array and see that how it can contribute to the A. And that's how I can solve the problem. Like I know that for a single cell, let's say for a single cell, the answer is always the value of the cell. Like for a single apple, what we have seen, like we have seen the case of two apple here, and let's say we just have one apple with value x, then the answer is obviously x, because one group will have sum equal to x and another group will have sum equal to 0. So for a single cell, we know that answer is equal to the value in the cell. And now if we find the value of the entire array without the current cell, then we can find the answer. So what's our base case here? For now, let's say I'm given two value to you. Like if somehow I calculate the value of a partition, and the value of first partition is sum1 and the value of second partition is sum2, then whenever I will reach the end position, like whenever I will complete the array and array become empty, I just want to find the difference of sum1 and sum2, and that's how I can define the base case here. Like whenever I will reach let's say I is equal to n, then I will just return absolute difference of sum1 and sum2. And now we know that for each position, it can be a part of sum1 and sum2. So I will just add this to sum1 and sum2, and we'll check that what's the minimum possible answer at the end. So what I will do, like I have one index I now, like which array element I am checking, and two values of sum1 and sum2, and sum1 is defining the sum of elements in the group A, and sum2 is defining the sum of elements in the group 2, and it's my function f that I will be calling. And whenever I will reach the index I is equal to, and I will just return the difference of sum1 and sum2, because I know whenever I reach this condition, I completed the entire array, and I just have to return the minimum possible computation that I know that so if I have sum1 and sum2, I just have to return the absolute difference between them, and that's what we want. So in the base case, we will just return absolute difference of sum 1 and sum 2. And from here, the recursion will not call itself again. And now, what there are two possible case. Like the first case is I put the current element to the group A. It means I will increase the value of sum 1. So whenever I put the first element into the group A, I will call the recursion function again by increasing index because I traverse the index from 1 to I, and now I have to calculate from the index I plus 1. And I will increase the value of someone by element I, A of I. And sum 2 will remain as it is because we are choosing the current element A of I as the member of group A. And the second case is like we are choosing the current element as the part of group A, and then we have to do something like this. We will someone will remain as it is, and sum 2 will be increased by A of I, and I want the minimum possible value from all possible case, and that's what. And so what I will do, I will just return minimum of first and second, and that's how I will complete like minimum of first and second is my answer, and I will return that, and that's how recursion is written, and I will get the answer of the array A, and that's what I implemented here. Like I'm reading the array, it's defined array P, so I named it pre, and I'm calling the function. I did one based indexing here, so I'm calling one and the current initial value of sum1 and sum2 is 0. After calling it, I did one based indexing, so I have to check n plus 1 here, and whenever I will reach n plus 1, I will just return absolute difference of sum1 and sum2. And what I'm doing, like it's my first thing, that I will increase my index. I will add my current element to the group 1, uh, and group 2 remain as it is. Otherwise, there will be second thing, like I will increase the index. My group A remain as it is, and I'm adding the current element to the group 2, and I just have to find the minimum of this, and that's how the magic will run. And like you can say that recursion is magic. You don't have to write the things again and again, and it will just compute it for you, and you will get the answer. And I added the link to the code as well. Like I got the AC to the problem. Okay, I'll do, yeah. Like I got the accepted verdict on the problem, and now you guys must be like thinking like what I was calling stack previously. So stack is a memory structure that keeps the function, that keeps the track of the function calls. Now let's see. I'm calling. Okay, okay. I was calling function here. Like from f of 2, I was calling 2. Then until f, the value of f of 2 is written to the written here, the computation of this function is go on hold, and the function f of 2 will run. Now again f of 2 is on hold and f of 1 is running. Again f of 1 is on hold and f of 0 is running. So after reaching f of 0, I am freeing these things. So there is a structure which we call stack in the memory. Like whenever I'm calling some function, it will go in the stack. Like let's say I called f of 3, so it goes in the stack like this. Now from f of 3 I again found that I'm calling f of 3, f of 2. So f of 2 is called, and whichever function is in the top of the stack will run. So f of 2 is running. Now I encountered that f of 1 is being called from f of 2. So now f of 1 will go into the stack. So this structure is storing the entire thing of the function. Like whenever f of 2 will complete its computation and the f of 3 will run again, then the variables at the function f of 3 will not be forgotten. Like after f of 1, now let's say I go to f of 2 and again it's computing f of 2. So it's a it's of no use. Like I already completed half of the function and now it's computing again. So whenever it start computing again, it will call f of 1 again. So in the structure, it will call everything like the pointers to the variable, pointers to the function, etc. in the memory. So that is called call stack. And each recursive call is added to the stack, and it contains like a local variable and return addresses and everything. And whenever the compute, like let's say array a is calling the function b is function a is calling the function b, and function b start executing. Now whenever function b stops, the function a will restart from where it was. Like it computed something, so it will remain as it is and it will be stored in this call stack. And again the function a will run and the things will go like this whenever the now from f of 1, like we know that we are calling f of 0. So whenever f of 0 is completed, f of 0 is removed. So the stack will become like this after the completion of f of 0, like f of 1, f of 2, and f of 3. And after this f of 1 will be removed, after that f of 2 will be removed, and after that f of 3 will be removed, and it will store the address where I have to return the answer, and it will be returned to the that address and saved to that variable. And you might have worried like why we have to take care of this. The thing you have seen in many of the code forces problem, like let's say yeah, like we have seen the memory limit is 512 megabytes for this particular problem. So whenever we are calling recursion and function are storing itself into the stack, now let's say recursion goes to the infinite and we forgot to define the base case or forgot to define the optimal base case, then the recursion will go to infinite and the stake space we are given is 512 megabytes. So once this stake will be filled to the memory, like the size of the stake goes to the 512 megabytes, it will run and then it will say like the stake space has been exceeded and it will return some fail verdict. And that's what the thing for your own local PC as well. Like in your PC, the memory is limited, and if you call a infinite number of recursion, then it will your PC will hang and that things will happen. So that's why we have to take care of the call stack as well, like how many times we are calling the recursion, and at max how many number of function will be there in the call stack, and what is the space complexity of each recursion. So these things needs to be taken care of when we are building recursive approach of the problem. And now let's see another important topic, which is backtracking. So let's see what is backtracking. Backtracking is a problem solving technique that involves defining solution incrementally by trying different options and undoing them if they lead to a dead end. Uh, the backtracking is mostly used whenever you are trying to explore all possibility. And whenever you find a position which is not useful to you, then you will go back to the recursion function which did that change, and you will undo that change and call the recursion again. And that's how backtracking will work. Is work. Like let's say you are building a string and you want to achieve string your answer. Let's say string t is equal to abc is your answer, and you are building string s from the empty state. So what you will do, like you don't know how to directly build abc, so you are trying like every possibility of string of size 3, and if it will take you to the answer abc, then it will return everything and stop recursion. Like until you find abc you will not stop. So what you might be do, like it's empty position, right? So let's say I put character a first, okay, and my string will become a. Now let's say I'm putting character a again, so my string will be a, okay. And let's say now again I'm trying to put character a, as I don't know what to do. So my current string is a, and what's my base case will be like if I reach the condition n is equal to 3 and string is equal to t, then only I will say yes, it's a valid position. So let's say I'm returning true if it's valid and false if it's not valid. So I'm returning false, or I'm returning true in this case, and otherwise I will just return false. If n is equal to 3 and s is not equal to t, then I will return false. And what I want to see, like if the false is written, it means my string is not correct. Then what I will do, like let's say after this stage, it will return false obviously. So what I will do, my function will go here, and now false has been returned. So what I will do, instead of a, I will now try to put b in that position. And now again my string will be aab, and again it will check and return false. So the false has been returned. So this function will now let's try to put C here, as we don't know how to build and we are just trying every possible way to build the string ABC. And that way I tried every possible things like A to Z for the third character, and I didn't get the success. So what I will do, I will return the false entirely after the computation of size 2, and after returning false here, it will get to know that I have to put another character at the position B, because if I get false for this, then it means that my second character was not true, because I tried every possible character for the third position. So again, I will try every character for the second case, and now I tried character B, and my string will be AB. Now from this AB, I will call again A, and my string will be ABA. It will return false. Now I will try B again, so it will be ABB. It's again not true, so I will return false. And now I will try the character C, and it reads the string ABC. and it returned true. So it means that AB was correct and C was correct. So from AB, it will return true to the position A, and from A, it will return true to the empty state. So it means that A was the correct choice, B was the correct choice, and C was the correct choice. And that's how I read the string ABC. So what we did, like we put something and again call the recursion function to the next position and trying to put another character. And after that, whenever we read the and we are comparing the string, and if it's not same, we are saying that yeah, my recursion was not correct and I will try from the last position. Let's say now I change the last position to something else and see again, and that doesn't work. So it means I will go back to second last position and try to change that to the every possible way, and to see that if you can achieve the desired thing or not. So that's how backtracking works. And to understand the backtracking, the best possible problem is, I think, n quiz. So let's try out that problem. Uh, uh, I think subsets will help to understand it in a better way. So let's see. You are given unique elements and you have to return all possible subset. A subset means the power set. Like here is the array 1, 2, 3, and here are the subsets of 1, 2, 3, like empty set 1, 2, 1, 2, 3, 1, 3, 2, 3, 1, 2, 3. And the number of the power set is equal to 2 raised to n, that we know. And the solution must not contain duplicate subset, and we have to return solution in any order. The output doesn't matter, like if we place 1, 2, 3 in some other place here, then it doesn't matter, it just have to contain all valid 2 raised to n power sets. And that's how, and that's what we have to do. So let's try to understand like what we can do in the recursion. So what's my thing here? Like now let's see the minimum possible case for the base case. Like if the array is equal to 1, then my answer will be empty space and 1. What we did for 1, we just put empty subset or put or take a 1, and the case is like if we have something smaller than this, like just empty array, then the answer is again empty array. And we don't have empty array, yes, n is greater than 1. So here is the smallest possible case. And now let's see what we can do. Like we don't know how to do, then we have to try every possibility. Like if I'm at position I, and you know, in the power set, some position might occur, some position might not. So if I'm at position I, then I have two possibilities. I can take the position I, or I do not take the position I. So if I take the position I, so let's say here is my previously built some set, and I'm adding AI to it and move to the next position I plus 1. And if I'm not taking the position I, then something like this will happen. Like I have some pre-calculated set here, and I'm not taking AI, and I'm moving to the position I plus 1. And that's how whenever we will, and for I plus 1, again, we will have two possible case, take and not take. And again, same things will happen. So we know that repeated computation is here. So the recursion is the one of the best way to do this. And now let's see, whenever I read the position and like I is equal to and I read, that means whatever the set I have can be one of the answer, because what I did, like I tried the possibility like take or not take, and I read the position, and that means I processed every element, and whatever the set I will have can be the can be in the answer. So what I'm doing, like the code will clear the things. Now let's say I have array nums. I'm going to calculate the array of array answer, and the current is my current set, that current set of element that I picked. So what I'm calling, like calling the function from the position 0, passing the array, passing the current uh, set of elements, and passing the answer. And now forget about this case. And what is the way that array A might be the element of the current set? So I'm just adding array index to the end of the state, and I'm now moving towards the next index. And from that index, again, what I will do, I will put it into the array A, and I will move to the next element again. And but after reaching the array A, after reaching the end position, what I will have? I will have every elements from 1 to n, because now let's see the recursion tree again step by step for a smaller array, obviously. So let's say array is 1, 2, 3, and I'm at position 0. What I'm doing? I'm calling the function. I'm first adding the element 1 to this current state and calling the function 1 again, going to the index 1 again. From the index 1, I'm adding the element 2 in the set. So my current set will be 1, 2. And I'm going to the index 3. From index 2. From index 2, what I'm doing, I'm adding the element 3 to the current set. So it's a 1, 2, 3. And I will read the and position n. And from these three, I know that whatever the current set is the one of the element of the power set. So I will just add it to the answer and stop my recursive call and move to the index 2 here. But from index 2, what I did, I added 3 to the current set. But now I want to explore that what I can achieve by not adding 3 to the current set. So what I'll do, I will remove 3 from the set, and the that will be 1, 2. And again I will reach 3, and I will add this to the answer. Now from the now this computation has been completed, and now I will return to 1. I'm not returning anything, like I'm just completed my function, so it will be removed from the call stack. And that's how the computation of function 1 will begin again. So now I added 2 in the set. So what I want, that I want to explore that I did not include 2. So it will be like current set is 1, and I read the position 2. Now again from position 2, what I do, I add the element 3, and I read the final set again, state again. But another case is I don't include the current element, and my current set remains 1, and I read the final position. Again from the element 0, I added a 1 to the set. So I want to explore things where I am not including 1. So I'm go with empty set and I will go at position 1. And now from position 1, I want to check that I add 2 to the set or do not add 2 to the set. And from the position 2, I have to check that I add 3 to the set and do not add 3 to the set. And I will read the end position here. And from this, I read the position 2. And again, I add 3 to the set or do not add anything to the set. So that's how I have 2 raised to n possible power set, like 1, 2, 3, 1, 2, 1, 3, 1, 2, 3, 2, 3, and empty set. Because for every position, we did two things. We explored the possibilities where I'm adding 1 to the current set, I'm adding AI to the current set, and I'm not adding AI to the current set. And in the code, if you see, I'm adding AI to the current set and running recursion to do further computation. And now I want to explore things where I'm not adding the A to the current set. And that's what I can do by just removing the last element, because here I added and here I removed that. And I again exploring the other stuff. And whenever I read the end position, I will just add to the answer. And here I just return answer. So that's how thing work in the backtracking, like you undone the change that you did to explore other possibilities. And the other problem is the n queen problem. I hope you understand. Okay. I'm seeing the chat now. Okay, please join. Okay. I will try to write in big fonts for now. Here is the last problem that we are discussing on recursion and backtracking to understand it in a better way. So the problem is n queens, and the statement is like we have given n cross n chessboard, and in this chessboard we have to place n queens such that none of those queens kill each other. Like here is one of the possible configuration you can see, like the chessboard is of size 4 cross 4. And if we place queens like this, none of will kill any other queen. And the other possibility for that is like this, like if you see, the queen will walk like in the x direction, in the y direction, and in the diagonal. So this queen is not blocking any other's way. Now for this queen, if you can see that here is its movement. For this particular queen, here is the way of movement, and it's again not blocking the path of any other queen, and that's what we have to achieve. Now let's comment that what is the one of the possible thing that we can do, and what we have to, what will be the, okay, yeah, do we need backtracking or do we need backtracking here or any other way to solve the problem? Like with a simple recursion, can we solve the problem? Like try to think that we need to explore every possible position of the queen in the chessboard. Like every cell has two options, that it can tag the queen or it cannot tag the queen to that cell. And after that, after placing the queen to one particular cell, we have to again check that is the configuration still valid or not. And if it's valid, then we will go to the next position. But then again, we will found that yeah, I have to remove the previous queen. Like let's say I'm mainly building the chessboard of size 4 cross 4, and I place one queen here. Now I know that okay, I'm zooming it. It's is it better now? Okay, I think it's better now. So let's say I placed one queen here. Now I don't know that I can't place a queen in the current row because it will again block the path of this queen. So I must have to go down to the next row. Now again, if I try to place the queen here and I will check that is it correct, and I will find that there was already one queen in the current row. Then I have to remove the queen from this cell, and now I will go to the next cell. Now let's say I place the queen here, and I will again check that is the configuration still valid, and we know that it's not valid because diagonally they are blocking each other's way. So what we'll do, we'll remove the queen from here and try to put it here. But now let's say configuration is valid. So yes, for these two queens, the configuration is valid. And we will go to the next row to check. And now I try to put the queen here, but it's not valid. So I will remove it. Now I will try to put the queen here. And now you know it's still not valid because it's blocking the way of this queen. So I will remove it. My queen cannot be placed here, and if I say my queen cannot be placed here, so I found that that the previous configuration where I put the queen into the third column of the second row was incorrect, and I have to change that. So I will now, after I found that there is no possible way in the third row that I place the queen, so I have to replace the queen from the second row to the some other cell. So now I placing the queen here, and now if you see the second, okay, now if you put the queen here, it's not valid. If you put it here, it's valid. So and if we try here, it's not valid. If we try here, it's not valid. So we'll go to the next. Okay, wait a minute. Okay, sorry. Yeah. If I try to put it here, it's valid. Now I go to the fourth row. Wait a minute. I think it's. I think it's fine now. And it's valid. And now if we try to put queen and in any of the cell below, then we know that it's not valid. So we have to remove queen from the cell. And now we know that again, if we try to move this queen to the any other cell, it's not valid. So it means I have to change the queen's position in the second row. And now I know that I can't change the position of the queen in the second row. So that's why I have to change the position of the queen in the first row. So what we have found, like we did some changes. After that, we found that the configuration is not valid and we want to undo the change. So that we can achieve by recursion and the backtracking. So we will try backtracking here. Now let's try to solve the problem first here. Like let's say I at the row I. So whenever I'm at the row I will try every column from 1 to n. I will try every column from 1 to n. And for that column, I will try to place my queen in that position. Like let's say I place the queen at the position column. Okay. So I'm at the position I, and I'm at the row equal to I, and choosing I'm traversing every column from 1 to n. That if it's possible to place the queen at the cell called row, right? And whenever I will put queen here, I want to check that is it safe to place the queen here, and how we can check that thing. Like let's say again, I'm what I'll do like from the if I'm putting the queen at the column at the row I, it means that I already put the queen at every rows from 1 to I minus 1, right? And for that, I put I put I minus 1 queens in the rows 1 to I minus 1. So what I will do from the current cell, I will just check the upward column in the upward direction and diagonal left and diagonal right. So found that if I put the queen there, because it's obvious that we will not put any other queen in the same row. So found a whenever we found a safe configuration where we are putting the queen into the row, then what we'll do, we'll just move to the next row and we will increase the row I to I plus 1. And again for every column we will check that is it possible to place the queen in that column for the I plus 1th row. And if it's not safe, then what we'll do, that's the thing what we have to take care of. Like every case, like let's say I'm checking that is it safe, right? Is this configuration safe? Uh, and I found that it's not safe. Then I will move to the next column. Then I will move to the next column. And at the end, if there is no possible way to put the queen in the current column, it means that I did mistake in the one of the 1 to I minus 1 rows. So I have to move back to the previous row and try to change the configuration of queen there. If I found another best configuration, then there is no problem. Like from queen here was the safe configuration and we changed that to here and again it was the safe configuration. But after placing the queen here, it's not possible to place queen in the fourth row. So what we did, like after we found that we try to change the queen in the third row. Again, it's not possible. So we try to change the queen in the second row. Again, it was not possible. So what we do, go to the first row again and try to change the queen to the another columns. So that we will do that if none of the case is possible, none of the column is possible, then I will just go back to the row I minus 1 and try things again. So in the pseudo code, what we are doing, like here is the function f, which contains some parameters that I need to take the stuff. If it reaches the row I is equal to n, it means I found the configuration, and I will just push that configuration to the answer. Right. Now, what other things we need that for the ith row? Now we found one parameter we needed, that for the ith row, we are traversing every column from 1 to n. So we need n here. Keep track of it. And for f1 to n, we will first what we will do, we will put the queen to the cell row column, right? And we'll check that is safe by calling another function that is doing the computation in the black box, let's say, and we are not currently interested into that function. It's calling true or false. Like if it's valid, then it will return true, and if it's not valid, then it will return false. So if it's a not safe, like let's say if it's safe, then what we'll do, okay, like if the current configuration is safe, then I have to increase my row that I know that I can't place the queen in the ith row again. So I will go to the I plus 1th row, right? And that will be computed. And like if it's not valid, then I have to move to the another column. So to move to the another column, I have to change the configuration of it to empty. Like I place the queen to the row call cell, but now again I have to change it to the empty state. And that's how my for loop will run. And now if I found that I didn't found any safe place to put the queen, it means that I have to go back to the previous row. It means I will go to the I minus 1th position again and check that is my configuration was valid or not. And I think it's better to see the code to understand it in a better way. So what I'm passing the okay the output, uh, like previously in the subset it was answer that I needed. The path, I want path because I'm just storing the columns in the path, so whenever I read the AND state I can create the answer again. And the board is n cross n board that we are building, and I'm passing n and 0, like, and I told you, and 0 is the number of row here. So what I'm doing, I'm traversing every possible, so I'm traversing every row and column. I'm traversing every column and putting the queen there. One means I'm putting the queen there. And if it's not safe, then I'm going to the row plus 1 again. If it's safe, then I'm going to the row plus 1 and pushing the I to the path. And it means that I choose the ith column in this move. And after solving this entire thing, like this solve function again call itself and the magic will run. And after that we might have to we have to find every possible, like in one row there can be multiple safe places. So that's why I have to pop back the path again. I have to replace queen with 0 again. and that's how my function will be run. And I don't have to call the function f my I minus 1 here, because whenever this function will run, it will go back to the previous function itself that we have seen here, that after running 3 we don't have to call the function I minus 2 like 2 here, because the recursion will go to the function 2 from the call stack. And that's how we implemented. Now let's see the details of each step. In the each step, what we need bond, the current row, the current column, and the n. And it's more than enough to find that the configuration is enough. So what we'll do, like in the upward direction, we will check that is there any queen in that column, and if we found any queen in the current column, which is y, then we will just return false. In the diagonal, we will check that is there any queen, or the diagonal can be left diagonal or diagonal can be right diagonal. And if we found any queen there, then just return false. And if we don't find any queen in three of these state, then just return true. And that's how each step is implemented. And whenever I reach the final state, I call the function make answer. That that's from path. That in the path, if I implemented included I, it means in the ith, in the jth row, like in the at the end, the size of the path will be equal to n, and the ith position of the path array denotes the number of row which I took for that path. So I'm just building the matrix here and adding to the output, and that's how the entire thing is implemented. And it's not more than magic, you can say. And it's hard to explain things on the paper, and you can try to explore things in the visual though. Like there are problems like GCD as well. Like you are trying to find the GCD of 17 and 19. You can see it's a recursive case that you call the B and A modulo B, and the other function is like you can do binary search, LC, and these are dynamic programming questions. And again, there is option of custom code as well if you want to do that and explore that how your recursion tree is running. And that's what that's it from the my side. I hope you understand the concept of recursion and the backtracking. And now if you have any doubts, and let me know in the chat box. I open the chat box in the another device. Soham Jail is asking how important is discrete maths for Codeforces. Okay, so discrete maths like integration and differentiation are not important for Codeforces. You just need basic knowledge of maths like GCD, LCM, modular theory, and other stuff like Euler-Thomson function. That's also a expansion of GCD's property and thing, and that's what all you need for the Codeforces. Okay, like I don't think you need too hard stuff to start with the Codeforces at the beginning. Uh, with some basic stuff that you already know from the schools will help, and the basic properties of them you can revise and watch some videos. Or we had the lecture of Surya Pandey, you can watch that because Surya Pandey explored the maths that needed to solve the problems, city problems. Some things were advanced there, but yeah, it was all you need to do with Codeforces. Okay, I think the attendance has not been done. Don't worry, we will just okay, we will just skip this lecture for the attendance, I guess. And any other question? Okay, I think no one has any other question. So I can end the stream. Can I add the string? Let me know. If you don't have any question, then you can just leave. Okay, the attendance form has been said. To grow in Codeforces, there is only one way. Learn every day, practice every day. Like, you don't need too much knowledge when you start with the Codeforces, just a basic implementation skill, and the practice of the implementation skill is all you need, and things will be learned along the way. That's the trick. I will share the PPT, and I don't think my handwriting was good to share the actually draw thing. So I will just share the PPT to you guys. I hope you enjoyed the. Okay, everyone, fill the form, and I'm ending the stream. Just let me know that can I end the stream or not. Ayush, battery of my earphone.